Okay, ladies and gentlemen, today we're going to start a mixture of topics, selected topics that I think are of interest to me and I think will be useful to you, especially if you go on, you take the Calc 1 or Calc 2. And that would involve some topics from chapters 13 and 14. One of them is sequences, arithmetic and geometric sequences. We'll probably do a little bit of probability depending on the time. Rather counting, permutations, combinations. This kind of stuff is real important. And maybe a short little piece on inductive reasoning, inductive proof, and things of that nature. Okay, today we're going to start off, I believe this is chapter 13, with sequences, aka progressions. Back in the old days, we used to call these progressions. Now they're called sequences, same thing. Okay, definition. Sequence, aka a progression, is a list of numbers arranged in a definite order. So in other words, there's a first, second, third, fourth, etc., and formed according to a definite rule. The numbers in a sequence are called terms. Okay, well, here we go. This says use the general term a sub n to write the first five terms of the following sequence. So if we're looking at the sequence here, okay, a sub n is called the general term, and you can think of that as the same as f of x if you're talking about a function. Now, when you're counting things, you start 1, 2, 3, 4, dot, dot, dot. So actually, a sequence is a kind of function whose domain, in other words, the numbers that are going in, um, are the positive integers. So we typically start with n equals 1, n equals 2, n equals 3, and that would be the formal definition of a sequence. Okay, so if n is 1, you get a 4. If n is 2, you get a 7. If n is 3, you get a 10. And you can see it's going up by 3's. The fact that if you think of this as a linear function, the 3 would be the slope. That's where it's coming from. Okay. Second example, a sub n, and this is the general term, is 2 to the n. So 2 to the first is 2, 2 to the second is 4, 2 to the third is 8, and then we go on 16, 32, 64, and so on. The general term here is n squared. So 1 squared, 2 squared, 3 squared, 4 squared, 5 squared, etc. So 1, 4, 9, 16, 25, and so on. Those will be terms of this sequence. Now, if you go onto Blackboard, you will see sequence notes plus. The plus means I've given all the solutions of the answers here. So you can follow along with that. Maybe that will be a little more helpful. Okay, this is called a recursive sequence, whereas these are called closed form. If I wanted the 100th term here, I'd simply plug in a 100. So the 100th term of the first sequence would be 301, 2 to the 100th power here, 100 squared to 10,000 here. However, here, to get the 100th term, you would have to go ahead and, well, let's talk about what this says anyway. It says the nth term equals the sum of the previous term, the n minus first term, and previous term to that, n minus second term. So this is a very famous sequence called Fibonacci, and if you start out with the first two terms of 1 and 1, then you would see 1, 1, 2, adding of those, and then 1 and 2 is 3, and then 2 and 3 is 5, and so forth and so on. Sequences fall into several categories. We're going to principally look at arithmetic and geometric, Fibonacci not so much, and you'll come across all sorts of interesting, strange ones in Calc 1 and Calc 2. Okay, let me show you a few examples of how you can actually plot these on your calculator. So first, let me show you an example. Here's a sequence, okay? And the nth term is 1 over n plus 1. And actually, notice the set brackets around it. When you see the set brackets, that typically means that you're not just talking about the nth term, you're talking about the entire sequence as a whole. So the entire sequence as a whole, I would start with n equals 1 and then go n equals 2, n equals 3, n equals 4, dot, dot, dot. So if n is a 1, I get a half. If n is a 2, I get 1 over 2 times 3, or 6th. If n is a 4, I get, 1 over, or rather, if n is a 3, I get 1 over 3 times 4, or 1/12, so forth. So these are the terms of the sequence, and the general pattern of the nth term is this. And notice I have dots after it, indicating it goes on, and I have dots in here, indicating that there's a pattern. We're not going to write all the terms, okay? So this is a plot of that, and you can see when these are the values of n here, 1, 2, 3, 4, 5 up to 10, and when n is a 1, I get a 0.5 from this chart here. When n is a 2, I get, what I get, a 6, 0.167 and change, so forth and so on. So let me show you how you can do this on your calculator. Okay, I'm working with an 84 plus, so what I'm showing you work fine on an 83 and the 83 family, and I'm sure probably in some of the others as well. Okay, first thing is you want to press the mode key and take a look at what we've got here. If you go down to the 4th line, you have functions, and these are typical functions with x's and y's, and if you scoot over here, you have parametric and polar, and SEQ stands for sequence. So we're going to want to be in sequence mode, and if we tool on down, we can either have our graph connected, or we can have just dots plotted. Sequences, as you can see, exist for n equals 1, 2, 3, 4, 5, dot, 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 but not for like n is 1.5 or n is 2 2/3, so we don't want it connected, we just want the dots. Okay? So this will be the first one we do. I'm going to go into y equals, and notice that it looks a little different here. Okay, if I were in function mode, I'd see y1, y2, y3. If I were in polar mode, I'd see r1, r sub 2, r sub 3, and so forth. In sequence mode, I see something different. Okay, so I'm going to start with n. N min is a 1. And we typically use a sub n. Some books use u sub n. It's the same thing. So u sub n, and I type in here. In fact, let me actually do the typing in for you. Bingo. Clear that out. You type in 1 divided by, because it's 1 over, and then you need parentheses because the order of operations, we want to divide by this entire expression. So now we want the n, and when you're in sequence mode, pressing this key here will give you the n. In polar mode, it gives you theta. In parametric mode, it gives you t. In function mode, it gives you an x. We're in sequence mode, so if you want the n, you just hit this, and then parentheses, n plus 1, close paren, close paren. Okay, so that would be how we enter our general term. The rest we're not going to bother with. You can do that for other situations later, but I'm not going to bother with this. Notice you have a UVW, so it allows you to plot 3 sequences at once. We're just going to do 1. Okay, we then go into a window key, and you're going to notice you have to have a little bit of knowledge here, right? N is going from 1 to 10, so 1 to n min is 1, n max is 10. I'm starting to plot at 1. I'm going in a plot step of 1. Okay, that's all pretty common sense. Now, as far as x min and x max, I mean, for some reason I put a 12 here. You don't like that, you can make that a 10. So, 10, whoops, wrong spot, am I? So, 1, 0 is 10. X scale, I'm going to count by ones here. As you can see, this is sort of what I'd like to get. Going down, y min and y max. Now, think of this as the y value. Y max is a half, but we know from experience that sometimes if we use trace or something along those lines, that some message prints out and obscures some of our graph or our picture. So I'm going to go y max is 0.6. And for the same reason, instead of going y min is a 0, I'm going to go y min's negative 0.2. It'll give me some room, and I'm going to go in steps of 0.1. So I'm going to have like a 0.1, 0.2, 0.3, 0.4, 0.5, 0.6 along here. Okay, and now if you want to, well, let's just press the graph key, and there it is. You see, since we chose dot mode, there are dots here, and as you can see, once we get past, say, the n is 3 or 4 or 5 even, these values are so close to 0 that they are not really showing up on the screen. You could adjust your window for that. It's up to you, okay? All right, so this is what we're doing. And now if I want to do a trace, I press the trace key. And as I promised, we need a little more room on the top to see the actual function, or in this case, the general term. And we need a little room on the bottom to show the values of n and the x and y values of where we plotted. So the first one is n is 1, and n corresponds to x, so we're not really going to worry about that too much. But look at the y values, a half, exactly what I got from my Excel table. Okay, and if I use the right arrow key, notice I get to the second value, n and x are 2, and I get 0.1666 and change. Okay, and I keep on going, so I can draw various plots. So this would be 1/12, I believe, 0.08 and change. It's pretty small. This is 0.1, so 0.08 would be just a little less than that. Okay, and you can see from my table of values here, and you can keep on going, and you can see where the little spider marker is. Okay, now you can also create a table. So we're going to go to a place called table set, which is right up here in blue. So second, table set, table start. We're starting at n equals 1. That's our variable. And we're going up in steps of 1. So we're going in as 1, 2, 3, 4, 5. So that sets up our little table. And notice the word table is in blue above the graph key. So I press second graph, and there's my table. And you can see that the values here, which I did in Excel, which you can do easily enough, roughly correspond to the values here. Okay? Now, if you're wondering, well, gee, how come I have much more accuracy here than on the calculator? Well, Excel is a pretty good system, but the calculator has actually that as well. So if I arrow over, okay, I notice that the value appears on the bottom, and if I arrow down one, you will see that I get a much more accurate, more significant figures for the second term. The reason why it appears less here is because I have a preset space which only allows, well, let's see, I got 1, 2, 3, 4, 5 digits in the decimal point, so it looks like it's allowing for 6 figures here, including the decimal point. So if you want a more exact value, you can simply get over to that second column and motor on down, and you can see that we're pretty much mirroring what I got here in Excel. Okay, so that's pretty cool. So let's look at another one. Okay, is that the one I wanted to look at? Well, okay, so here, you could have an alternating series. You have -1 to a power, you raise -1 to a power, and what happens is the signs flip back and forth. So, you know, that could very much happen. Here we have a sequence 2n minus 1 over 2, and by putting in the numbers again, we're starting with n is 1, 2, 3, 4, 5, so forth and so on. You get these values, and dot, 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 because there are numbers here that we're not going to show. Here's the general term, and dot, 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 there are more values afterwards. This is important. Okay, you got to have those dot, dot, dots here to indicate that it just doesn't end here. It goes on and on and on. Okay, so if I plug in a couple numbers, let's say n is 1, I get 1 over 1, or, whoops, I can't see that, so let me shrink this down a bit. Okay, if I plug in n is 1, I get 1. If I plug in n is 2, I get 3/2, 1 1/2, n is 3, I get 5/3, so forth and so on. And as I plug in larger and larger values of n, this seems to be getting closer and closer to 2. So if you see a picture of this type, the 2 here we call the limit, and we've also called it horizontal asymptote when we were working with functions. So this is a nice way of picturing and seeing what's going on. You can actually see the asymptote. Okay, so let's see what else we have. Oh yes. Okay, here's an example where we have an n squared on top, a 2 to the n minus 1 on the bottom, and the n squared is pretty big, but what happens is the denominator eventually 2 to the n overpowers the n squared and it pulls it down. So it's very possible that you would see pictures that look like this. Okay, and you can do this on your calculator, just make the suitable adjustments for the window and everything. One thing I wanted to show you, let's see if I can find it. Yes. Okay. Um, this is a limit which you've heard about in the past. And the sequence comes from 1 plus 1 over n to the nth power. And it turns out this is the most famous limit ever. It turns out to be e, and you will learn later on that e is not, in calculus rather, that e is not just some made-up number that somebody devised, 2.71828, 1828459045 to 15 decimal places. Somebody just didn't make that up. It's a natural, that's why it's called the base of natural logarithms. It's a natural product of growth. If you take this as your sequence value, and these are symbolized by the red dots, because the sequence is discrete, whereas something like this is a continuous function, you get the blue curve, and you start plugging in numbers, you can come up with a table of values, which I did. Okay, and it goes very slowly. If n is 10, 100, 1,000, 10,000, 100,000, a million, these are the values that this expression, this general term approaches. And you can see this is looking like E. Okay, and it is E. And it's very close, and we'll actually prove this if you take a class in Calc 2. We'll actually prove that this turns out to be E. So once again, you have ideas playing out here. Which you've seen before. You got the idea of horizontal asymptote, you got the idea here of a discrete sequence, and the function which goes through all those points, which is continuous. Okay, sort of like beer and peanuts. Peanuts are discrete. We count them. We have 1, 2, 3, 4, 5 peanuts, but beer is continuous, right? We don't count that. So alright, so that's pretty much what I wanted to do for you with sequences for the time being. And then we're going to go ahead in the next video and we're going to talk about arithmetic and geometric sequences. Okay? So if you have Blackboard, you should print out sequence notes. And if you want to have a lot of these solutions written out, Sequence Notes Plus. All right, so we're going to do a bunch of examples starting with these next video. Thank you.